Let's talk a little bit about black body radiation. Specifically, we're going to talk a bit about Wien's law and the Stefan-Boltzmann law. When a charged particle accelerates, it gives off electromagnetic waves. The greater the acceleration of the charged particle, the greater the energy and therefore frequency of the electromagnetic waves. Due to the relationship between frequency and wavelength, the higher the frequency, the shorter the wavelength. Atoms are composed of charged particles. Therefore, the vibrating atoms in objects radiate electromagnetic waves. As we know, the atoms in a hot object vibrate faster than the atoms in a cooler object. Therefore, hot objects radiate shorter wavelengths than cooler objects. This diagram is meant to represent an atom in a hot object. It's vibrating very, very rapidly. Therefore, the frequency of the electromagnetic radiation given off is very high, and therefore the wavelength is short. So hotter objects radiate shorter wavelengths. This atom is in a cooler object. Therefore, the acceleration is not as high. Therefore, the frequency is lower, and therefore the wavelength of the electromagnetic radiation given off is longer. All the atoms in an object are not moving or vibrating at the same speed. There's a distribution of energies. Some of the atoms are moving more slowly, some of them are moving more rapidly, but in a hot object, the average speed is going to be higher. This is a hot object. Notice that the peak is at a relatively short wavelength. But also notice that since not all the atoms are moving or vibrating at the same speed, we have some atoms that are moving very rapidly, and those have very short wavelengths, and we have other atoms that are moving more slowly, and they have longer wavelengths. So what you end up with is this distribution of energies. The spectrum shown in green here is meant to represent a slightly cooler object. Notice there's two differences between the green graph and the blue graph. The peak in the green graph is shifted to the right, which is a longer wavelength. So the green graph represents a cooler object. One difference is the peak is at a longer wavelength. The second difference you'll notice is that the peak is lower. The peak for the blue graph is up here. The peak for the green graph is down here. What this is saying is that at lower temperatures, the amount of energy being radiated is less, the power is less. That relationship is described in the Stefan-Boltzmann law. In this graph, the red line depicts an even cooler object. Notice that the wavelength is even more shifted to the right, i.e. it's a longer wavelength, and notice that the peak energy is even lower. So one of the things that you'll notice when the temperature of an object becomes cooler is that the peak wavelength, as determined by Wien's law, becomes longer. Cooler objects have longer wavelength emissions. And the second difference, determined by the Stefan-Boltzmann law, is that cooler objects give off less radiation. The power, the watts being emitted, is going to be lower for a cooler object. Okay, that's all. I hope you found this helpful. See you later.